Okay, hopefully you're all caffeinated and ready for this session. Hopefully you guys can hear me, right? Yeah. Hopefully you got to see some good demos outside and also interact with the SiFive team and our partners. So my name is Jahur Vora. I'm based out of Austin, Texas. I run our FAE team at SiFive. And I'm going to spend the next 30 to 40 minutes talking about SiFive Intelligence and how you can use our intelligence cores to accelerate the realization of AI and ML in your applications. So I think Drew touched upon this slide, but I think the important takeaway on this slide for me is that we have been working on RISC-V. The core team at SiFive has been working on RISC-V for the last 13 years, right? The core team started back in 2010. We founded SiFive in 2015. And then over the last 8 years, from 2015 to 2023, we have invested a lot in developing a complete portfolio of products. So as you can see, we have the essential cores, which are our embedded controllers that can be highly tuned, highly configured based on the markets and applications you're designing to. We also have high-performance AP or application class CPUs. And as you can see, we are on our 4th generation there, every generation delivering more performance, more feature sets in these microarchitectures. And then over the last couple years, as RISC-V gets traction in the market, especially automotive has become a key area for SiFive. And we've been developing products in the automotive space, which Andy is going to talk about after me. But I guess where I will focus today is the X200, which is a SiFive Intelligence processor. So this is an AI processor designed for not only the edge AI application, but also data center, right? It's a 64-bit application class CPU with a decoupled very wide vector engine. The vector engine that we've implemented today implements a vector length of 512 bits. And we have a roadmap that goes beyond that to deliver more performance. And we can certainly discuss that as you engage with us. So I guess in terms of AI, as AI is fairly pervasive in a lot of markets these days, right? So if you look at text, speech, computer vision, they're becoming mainstream, right? We are also seeing the rate of innovation in AI is pretty high. The models are evolving very fast. And then customers need to build solutions which are flexible, which can scale based on the innovation that's happening in this space. You still want to be able to maintain efficient implementation and realize efficiency in the hardware and software that you're deploying for AI. So focus on efficient AI is key. And that's what we have designed the X280 to deliver to. The X280 core has been optimized for modern AI workloads. It's highly optimized in that we have, not only does it provide the standard RISC-V vector extensions, but we have added SiFive custom extensions for AI. So these allow customers to support the various data types. For instance, if you want to support bfloat 16, we enable that. Quantization, we enable that. We have extensions that we have implemented in the design so customers can realize AI applications through the X280 core. It's also, given it's a 64-bit apps core with wide vector unit, it makes the design of AI solutions highly efficient and highly simple. As we engage with customers, what we have seen is customers typically today deploying AI tend to do a lot of hardware accelerators. Typically, they have a small scheduler that's driving the hardware accelerator pipeline. A lot of time, customers have to do a lot of pre-processing before data goes into the AI pipeline. And as we engage with customers, what we realize that the very wide vector unit and the X280 architecture, which supports very high memory bandwidth, a lot of outstanding transactions on the memory interfaces, allowed our customers to closely couple the X280 with AI hardware accelerators. And that RISC-V vectors lends itself very well to accelerating AI workloads. Given that you can gang multiple vector registers to form a very long vector, a single instruction can operate on a very long vector, right? So thereby it makes it very efficient, very low power. we were very pleasantly surprised in terms of the number of design wins we have with the X280, and I'll show that in the slide coming up. The other thing is, AI needs to scale, and you need to deliver a processor that scales in terms of the ability to deliver the performance for a variety of different markets. So we started with the X280 as a single core initially, and then as we engage with customers, we're able to deliver more performance through a very scalable implementation. So the X280 scales from a single core all the way to 16 cores. You can scale the memory bandwidth as you add more cores through multiple clusters in the design. Today, we see strong momentum in how the X280 is used in image processing, and as well as data center applications as well. So if you look at image processing, it's all about efficiently moving data, but also providing the performance and kind of managing cost in those applications. Latency is critical in terms of how the compute gets done and where it gets done. With image processing, we need to support multiple resolutions. So we need to be able to move large amounts of data to the vector core, enable processing on the vector core, right? So the scalable solution that we have and the high bandwidth that we offer on the interfaces allows the customer to do a lot of pre-processing before the data goes either into the X280 vector pipeline or through custom instructions, customer can process those through their hardware accelerator. And then again, wide vectors again lend themselves very well in terms of being able to manipulate imaging data. So as we engage with customers, we're working on roadmap products that scale beyond what we have today. Sensor fusion is all about latency, right? So again, latency, but also being able to configure the core to hit the power and area constraints that customers have, typically in sensor applications, right? So with the X280, although it's a 64-bit core, it can be significantly customized to kind of go into markets with, where it's being used in front of sensors. So we're able to kind of enable the configurability needed in applications like sensor fusion and being able to interface to data coming from sensors and be able to meet real-time characteristics that are required for that market. Aerospace and Defense. So again, we work with the X280, but typically this is also used as an apps core with very wide vectors. So the attractive part here is that it's a 64-bit core. It can run Linux, and it can run standard software stack. But there is a lot of investment and development happening around RISC-V vectors in general. Applications like FFTW, Open BLAS libraries are being developed by the RISC-V ecosystem. So the fact that you have a high-performance RISC-V scalar core that can run your standard software stack, but also leverage the efforts that are happening in the ecosystem around vectors, make it very attractive. The other thing with Aerospace and Defense is, given it's an open standard, these designs have very long life cycles, it makes it attractive for RISC-V vectors and the X280 being deployed in these markets. So with data center, typically as we engage with customers, what we realize is there are a lot of systolic arrays and custom compute engines designed to accelerate AI workloads in the data center. Typically, you have a small scalar core with its own tool chain that is difficult to maintain, right? And then you have customer had their own vector engines along with their own systolic arrays or matrix multiplication unit. So there was an opportunity here to kind of consolidate the different compute requirements on the SoC. So we work closely with our partners in developing a vector coprocessor interface that enable them to consolidate the multiple processing streams that were being deployed on the SoC. So the V6 interface essentially allows you to attach a custom accelerator to the core in a very low latency manner. Typically, customers have done this through memory mapped accelerators, which are hundreds of cycles in terms of latency. With V6, typically the latencies were reduced to tens of cycles from being hundreds of cycles. The other value in this paradigm was also the ability to make it easy from a software programming standpoint. So being able to use a single instruction stream that can target the scalar pipeline, the vector pipeline, but also instructions targeted for custom accelerators was very attractive to the customer. So this slide demonstrates the activity and the design wins that we have with the X280 in a variety of different markets. So if you look at the first one, today the X280 is also used for instance, in mobile devices, where customers are essentially using it for a lot of computer vision, image processing, image enhancements type application. It's also being developed in the same company in the AI data center application as well. The X280 is also used in a storage engagement where the customer is essentially using RISC-V vectors and AI to accelerate search in disk drives, for instance. And then the automotive use case are around sensor fusion. So customers typically manipulate a lot of sensor data, LiDAR, radar, and image data, camera data, where essentially they have their own accelerators, but the X280 with the vector pipeline was key in terms of being able to implement a more flexible solution, whereby instructions that were geared towards custom hardware, like convolution, would execute on custom accelerators, but then activation functions like softmax could be offloaded onto the vector core. You typically also, before feeding data to the AI engine, you have to do a lot of pre-processing before it goes into the AI pipeline. And that's where, again, the flexibility that the vector ISA provides and the wide vectors that we've implemented in the X280 was key for those customers. FPGA has, again, a very wide customer base, right? So being able to use the vector ISA and leverage the vector ecosystem in FPGA markets was key for the FPGA customers that we have. And then I think Jack and Drew highlighted the wins that we have with aerospace customers and NASA specifically, where the use case was, being able to run a variety of different workloads on a standard application class processor. But given that we have very wide vectors, you can run applications like BLAST and linear algebra in a low power manner on the X280. So X280 enables flexible computation, as you can see in this chart, right? Typically, as I said, you have an apps core, you would have some sort of DSP or a vector engine, and some sort of a DMA that moves a lot of data around in the SoC. X280 essentially allows you to kind of efficiently implement the processing streams through a single core, whereby the 64-bit apps core with MMU can run Linux. If you configure the core accordingly, it can also run RTOSes or bare metal software. And then the vector unit can be used for a lot of the regular vector programming or leverage the libraries that are developed by SiFive or our ecosystem. The key here is being able to provide high bandwidth data movement into and out of the X280 core. Again, the value here is a single ISA, a single tool chain with open software, right? So it kind of enables our customers to simplify the way in which you are programming for these devices, where you're not programming for multiple disparate ISAs or architectures like DSPs and embedded cores. So unifying the processor and the memory system opens up the opportunity to reduce area and power for the SoCs, but also kind of improve the productivity of the teams that are deploying the solutions. Again, so this is kind of going in more details in terms of how the X280 with the vector core processor interface can be deployed for AI markets. So typically, when they're deploying hardware accelerators, they're essentially doing matrix multiplication operations or systolic arrays, which are fit for doing convolution. But then a lot of times, as the algorithms evolve, you need the flexibility and programmability that typically isn't afforded by fixed function hardware. So that's where the X280 with the vector programming with wide vectors becomes attractive. And then the V6 interface essentially allowed the customer to attach and integrate the accelerator very closely to the vector register files. So typically, as I said, hardware accelerators typically have been integrated with processors through memory map interfaces. These are high latency, right? So with V6, the latency typically gets reduced from hundreds of cycles to tens of cycles. So that's one of the key benefits of the V6 interface. The other key advantage is high bandwidth, right? You want to be able to move lots of data through the accelerator in a low latency manner and deliver high throughput on that interface. So essentially, the accelerator has 10, 24 bits of data that it can consume from the vector pipe and the vector register file and write results back every cycle. The interface was designed to be a decoupled interface. So depending on the accelerator, it can be like a fire and forget or a push-pop style interface as well. Okay, so let's look at a little bit more in details on the X280. So as I said earlier, the X280 not only implements the standard RISC-V 1.0 specification, but SiFive implemented custom extensions to help accelerate AI market and AI applications. So to that effect, we have various forms of fast matrix multiply instructions that are incorporated into the design. We have quantization instructions, and then we have instructions that enable various data types and data formats. In terms of the vector microarchitecture, it implements 32 vector registers, each 512 bits wide. RISC-V vectors are vector length agnostic. So essentially with LMAL, you can gang many registers or up to 8 registers to create a very long vector which can be 4K bit or 496 bits wide. So essentially that allows you to kind of efficiently do the compute in a low power manner. Also reducing your code size and being able to better utilize your iCache, because now fewer instructions are operating on very wide data. On the scalar side, we have a dual issue in order scalar core. So this is typical of what you would expect. It's Linux capable, supports virtual memory, supports the hypervisor extension, and then it has a tiered cache hierarchy. So there's a level 1 cache, a private level 2 cache, and a last level L3 or level 3 cache. The core can be configured in a multi-core configuration, right? So in this case, you can configure a single cluster of 4 cores, or you can scale to 16 cores with 4 clusters. When SiFive delivers the IP, we provide a lot more integration than just the processor. So in this block diagram, when you configure the IP, not only it includes the CPUs, but it includes all the other system IP that you need to run workloads. So for instance, we have the HCA, which is a hardware crypto accelerator. So optionally, you can integrate that with the core. We have local and platform level interrupt controllers that are part of the design. So when a customer configures the core, they can configure the interrupt controllers. We have a bus error unit in the design. So this is responsible for managing bus errors, ECC errors, for instance. And then debug and trace, which is key as well, especially when you are deploying applications across many cores. So the debug and trace unit is typically configured by our customers to support capabilities like multi-core debug, multi-core trace. And then we have a small cache coherent NOC within the cluster. So that is responsible for maintaining hardware cache coherency across all the caches. In terms of the interfaces, we support many different interfaces into the SoC, which are standards-based. So these are based on AXI or Embassy HI. So if you want to scale the design with a cache coherent NOC outside and go beyond the 16 cores, essentially the cache coherent NOC interface allows you to do so. We also have a front port, which is essentially your I/O coherent port. So if you have bus masters which need to coherently access the cache hierarchy in the design, the front port enables the customers to do that. And the last but not the least, the V6 interface, right? So the V6 interface comes out of the vector pipeline. And essentially, it exposes the vector register file and a custom opcode space. So customers are able to develop either their own custom instructions to augment the core, or can attach accelerators through that interface, which is very wide and provides high throughput. So on the scalar side, as you can see, the scalar core is very performant. On smaller workloads like core marks and drystone, we hit 5.8 core marks, 3.3 drystone. But even on a larger workload, right, which runs out of DDR, for instance, spec in 2K6, we hit about 4.5 spec in 2K6 per gigahertz, right? So you can see the scalar core is very efficient, very performant. And then we've implemented int8 matrix multiplication instruction. So it can essentially do 128 matrix multiplication operation in a single cycle. So essentially a single core can deliver up to half a top running at 2 gigahertz, right? So when you configure the core into an 8-core configuration, typically you get about 4.8 tops just within the core itself. So that's, again, depending on how the core and what AI markets is being deployed at, certainly for small embedded AI application, the X280 can be used self-contained as an AI accelerator. But again, it's given the flexibility that we provide with the architecture, you can certainly scale the core and very easily attach hardware accelerators to kind of deploy AI solution. The memory system is a tiered memory system. It is configurable. So we have a tiered 3-level cache hierarchy, but we also support local memories. So if you don't want to run out of a cache hierarchy, for instance, if you have streaming data coming in, we have a low latency interface into the core that allows you to attach large SRAMs. So thereby it enables you to attach scratchpad type memories very efficiently if your workloads are not very cache friendly. So it's very flexible in that way that it can support a variety of different use cases. Okay. As I said, so we scale the design up to 16 cores, right? So it gives you a lot of flexibility in terms of the SoCs that the X280 gets used in. We implement cache coherency across multi-clusters, given we have a cache coherent NOC in the design. And today given the MMU, we run Linux out of the box on this design. So it's very flexible in terms of the options it enables for integration, but also software development. We see customers today using the X280 in the data center through custom instructions and custom accelerators. But then in some markets, it scales to very tiny, low-power applications as well, where customers need a small application class CPU that can also do some inference. So depending on how the core is configured, it scales to address a lot of different markets and use cases. Okay. So what about software? So with the hardware that we provide, there are multiple ways to program the RISC-V vector processor, right? So again, depending on the effort versus the results that you desire, starting on the left, we have an auto-vectorizing compiler, which is based on LLVM. So if you're happy to go in and restructure your code, typically the auto-vectorizing compiler does a decent job in terms of being able to vectorize vector applications. We're also investing in vector libraries. So at SiFive, we have vector libraries for signal processing, for linear algebra, so accelerating applications for BLAS, FFTW, nonlinear functions, and NN operators as well. So today we have about 90% of the operators that are available in TF Lite that have been optimized for the RISC-V vectors. We also have, as you can see the demo outside, we have a reference implementation with TF Lite as well running. So again, that's to demonstrate that X280 by itself can execute TF Lite models. And then we have SiFive Recode. So this is a compiler toolchain developed that makes it easy to port applications that are developed on other SIMD architectures. So today it supports moving applications and migrating Neon Intrinsics to RISC-V vectors. And then finally, Intrinsics. So if you're happy to optimize specific routines to deliver the best performance, RISC-V vector Intrinsics can be used to achieve that. Okay. So today, SiFive Recode initially supports the Neon to RVV Intrinsics. There is a compiler flag, right, that you can essentially use to compile Neon Intrinsics into RISC-V vector Intrinsics. Finally, in terms of the toolchain, along with the SiFive kernel library, which is targeting multiple different applications and multiple different markets, we are also investing in a compiler backend. So there are a lot of ML compilers like Google's OpenXLA, Google IRI, MLIR compiler toolchains. So we're developing hardware backends, compiler backends, that target the RISC-V vector and more specifically the SiFive X280 processor. So this is work in progress. We continue to collaborate with the open source ecosystem and our partners so that we can deliver solutions, software solutions for AI that are more flexible, that can support the many frameworks that customers use, from TF Lite to Onyx to PyTorch, so on and so forth. Okay, so SiFive Intelligence delivers higher performance. It has RISC-V vectors, it is also being used for efficient AI data flow processing. So it enables a lot of flexibility in terms of how you integrate that in your AI solution. The optimized vector computation unit with long vectors can be used to realize your AI solution. We have roadmaps that extend the vector width beyond what we have today, such that we can keep up with the changing computation demands that customers have on vector processors. And then finally, the ecosystem is evolving rapidly on RISC-V vectors, right? So OpenCV and other frameworks are developed by the ecosystem that are coming around very rapidly. SiFive is investing in software libraries, and then given the MMUs and the feature sets that we support in the core, standard Linux is available today to run on these cores. And then this is RISC-V compliant. Both the scalar pipeline and the vector pipeline implements RVV 1.0, thereby giving you the ability to execute scalar and vector programs on the SiFive Intelligence cores. So SiFive Intelligence solution, it's there to simplify your SoC designs for AI, right? It enables to reduce complexity and system resources. It provides you the opportunity to kind of reduce power and deliver performance in SoC designs around AI. It's based around open software standards. You're able to leverage the ecosystem efforts around RISC-V vectors, but also standard tool chain and standard programming model, Linux, Python, so on, right? It runs on the scalar core with the RISC-V vector architecture. We engage with customers and we continue to innovate on this architecture. So as you've seen, we've implemented the V6 interface. We have delivered a multi-core, multi-cluster design. So we continue to innovate on the vector architecture. And as we engage with our customers, we take their feedback and improve the processors. One example there being the custom AI instructions that we've added. So we continue to look at market requirements and bring those innovation into our vector architecture. Okay, thank you for listening.